nevertheless, we will do what we can.
It will be better than the last time.
Better than the last time. Last time was, yeah, I'm amazed that we spent that much time. We spent almost 2 hours in freezing cold. It's like, and one of us was not even like they were in shorts. Where remember Kelly was in not wearing full jeans. Yeah, the company was sufficiently enticing. Hello, Niranjan. Oh, I have to do this. There is a homework 11, I think. Did you guys see this in time? I posted it not on Monday, but posted on Wednesday. If no one realized it, that's okay. Have you guys checked it out? Maybe you guys will last.
It's over.
It's, oh, you did check it. Okay, it's available. Oh, so you 7 Monday, and that's 1 week from Monday. Like, of course, next week is holiday. It's right after that. Uh, the final exam at the X. Right. Good. To be take home. Like what I do is if there are 6 questions, 2 will be take home. No, 2 will be in class, and about 4 of them will be take home, and 2 of them can be finished in half an hour or something. So,
After the final exam.
what after the final? This is yesterday's discussion.
No, I thought we can go on.
Yeah. So yeah, I didn't pay too much. Oh, okay. So the suggestion is that after the final exam, you like Aryan and Abdullah are missing out on Monday's our grand hangout, so they want to hang out after the exam. Do you? How many exams do you have on Friday? Just this one. So then I can take you guys for lunch, however. Reasonable, all of you guys, I can take you up for. The only challenge is that I have an exam I'm giving at 2:45. I can ask my PA to do the job. So yeah, at 2:45 I have an exam. So I think wherever we go, I don't think it will take that long. like 8 to 10. If we have a brunch kind of thing, so let's say 10:30 is 11, I don't know what restaurant will be open. And we come back, I think even if we go at 12 about that, I think we can make it by 2 o'clock.
Yeah.
Reasonable. And I can give a backup time, ask Shannon or someone to, in case.
We can go after the.
Yeah, but the point will be, what will be the open place at 10 o'clock, you know? Do you guys know what you want to do? How about it? You guys discuss among, do you guys talk to each other at all? Huh? Do you guys have a WhatsApp group or anything?
Yeah.
You have, okay, good, okay. Yeah, so discuss this on them and what do you guys want to do? I'm open with anything, I can fund the lunch. We should have department giving money for each course, right? Like, to take on, take out kind of.
I think you want to send them a message.
Say that again?
And you know, John,
Oh, we should have Niranjan also, yeah, how does he join? I don't know.
I think you send a message.
Oh, he sent a message. Oh, yeah, Niranjan, you have a suggestion?
For the brunch.
Yeah,
I used to go to Thai. What is that? Thai place.
high taste, high taste.
I don't know if they are open at the
No,
time.
they're still there, they're still there. Yeah, you said that,
Say that again.
is that your suggestion?
I like that place and Indian place also.
Indian place, which one was this? Probably a near time.
Uh, I remember I went with you once. And what? Who is that student? You had a.
Yeah, that was Rimas. Yeah.
Oh yeah,
that-
yeah, yeah.
That is closed, unfortunately.
Uh-huh.
They
Oh,
were there a long
I see.
time, almost 25 years here and they closed, yeah.
I see.
So, yeah, that was a, but we have an Indian restaurant these days, it's called Bombay Early. Also good, it's just the other one was more, what do you say? It was there for 25 years, that is the only thing, I'm not saying it is good or bad, relatively speaking, it's just. So. Yeah, are you there, are you also there in their group?
No.
He's
Me?
not
No,
I-
no. They did not
Yeah.
invite me.
there. Yeah, so will you be able to make it on
When
Friday,
is it? When is it going to be, Dr. Sajesh?
December 15th?
I will think about it.
I think that's correct.
I would like to talk to you guys and have something together, lunch or something. Yeah, we'll try.
No, that's nice. So we'll do something, yeah, okay. So Thai taste is a suggestion, but you guys discuss among each other. Last time it was something nice, I think last time or 1 year back, you were there, Arjun, right? Was anyone else?
Korean food?
Yeah, the Korean food. So we had Maz, who is from Carbondale, so he knew some places, and he said there was a truck, a Korean truck that recently started. He was very interested in. I think it was a nice,
Yeah, that's good.
nice idea. Yeah. So I had never tried it, and it was really nice. Yeah. So come up with something that you guys want to try out, and we'll put the bill to the university. Maybe we'll try it. They may not buy my argument, but we'll try it. That this is good for the students. Like take away the stress of the exam week, right? That's an argument. But yeah, okay. But no one is going home or anything, right? That's the last day. So if it's the last exam, Nathan, you're from around here, right? So it's very tempting to go home. Maybe. Okay. Okay. So you guys are all good. So I might be the one who is running away. So I'm traveling on Sunday. So probably I'm the earliest. Yeah. Okay, so we'll do something at after 10. Let's decide on the time after Thanksgiving. Or we can discuss this on Monday. Oh, Niranjan, you're also invited on Monday. On Monday, we are going to Giant City for lunch.
Like coming Monday.
Coming Monday, yeah, thanks.
I wish I can.
I know. Yeah.
Thank
But
you.
Yeah, just for your information, yeah, by any chance you end up here, if you're traveling and you're going this way.
I will try definitely December 15th.
Yeah. Okay. Okay, so let's do something. I want to wind up on the Green's function. I want to also give a small feel for what we are doing here in a broader perspective. I just talked to Aryan about it. I think he was asking, and this might give you a bigger picture of how Green's function fits in there. So notice, like typically we do special functions. And why special functions? They're usually geometry related. We are talking about configurations. Let us say there is two metallic plates in electrostatics, or for that matter, if you're doing gravity, there are two planetary structures which are planar. That never happens, I think. But if you say your universe boundary is like a plane, you can always talk about that, at least propose that. Then you will have to solve it, and then you talk about planar geometry. But electrostatics is the best planar charge distribution. The other is cylinder geometry, and the other is sphere. And believe it or not, there are very few problems you can solve exactly, and they turn out to be these three. In fact, even cylinder is very hard. If you talk about electrostatics, cylinder is too hard. Or maybe I should say, if you go to dynamics, if you include the frequency also statics, and if you include the dynamics a little bit, cylinder is too hard. So planar and spherical is the only reasonably easily solvable geometry. Whenever it is solvable, there is a differential equation, and differential equation has a solution. Right? In this case, this is exponential, e raised to I a, k is some constant, and that is exponential of minus I, right? Sine and sine. So these are exponential functions. Right? You can say, what are the spectral functions representing this? Fourier functions. Okay. In cylinder, these are Bessel function. Since I have not introduced it, it's not very useful to write them down. These are Bessel functions. And I should also say that it's best, like usually there are three directions, right? If you think of a cylinder, there is a radial direction, there's a z direction, and there is a circular direction, right? Each one of them has a function associated with it, and I'm talking about the radial direction in this case. In sphere, this is spherical, so maybe I could say Bessel functions plus exponentials minus plus or minus kx by plus or minus kx, and in this and plus, right, and plus e raised to I and x. M is the order, like the circular theta. So this is z and let's not go into the details. Like I think let's just I'm giving an idea, right? Let me not go into the spherical harmony. The basic idea is that given a geometry, there are solutions for the geometry which are described significantly better in terms of these functions. It doesn't have to be in this function. You can work in any special functions you want. In planar geometry, you can work with Bessel functions. In planar geometry, you can work with spherical harmony. Nothing wrong. It's a complete set of functions, but it's convenient to work with it. There will be a lot of simplifications if you work with Fourier functions instead of spherical harmonics in planar geometry. Same thing in the opposite. If you are working on a sphere, you can always work in Fourier functions, but spherical harmonics will give you an advantage. It will be very convenient. Each of these are having differential equations associated with it. And what we have been doing is the planar geometry, where these are solutions. So we have not been using x, we have been using, let me write x so this time. It's x squared plus instead of omega squared, like k squared. And the solutions here are e raised to I kx and e raised to minus I here. Right, so I'm writing this as both at the same time. Both of them satisfy the solution, and that's equal to 0. If it is 0, that's homogeneous solution. Right. If it is not 0, then that's what we have been working with, right? So let's say this is a of t or a of x now. Now change this differential equation, make it the differential equation for Bessel equation, and the whole idea of Green's function that we did goes exactly. Exponentials get replaced with Bessel functions. Exponentials get replaced with spherical harmonics. The ideas are exactly the same, just your unit vectors have changed. Like you work in rectangular coordinates, I hat and j hat. These are like that. Now you work in terms of Bessel functions. There are two solutions. So that's what we will do. Then after Thanksgiving, we'll come in the first day. We'll introduce Bessel functions, what they are, write down the differential equation, and then immediately say, what if there was a source? What if there was a source? How do we solve the Green function? And in fact, you will notice that everything will remain the same. Same Wronski and everything will remain the same. Just the functions are different. And because there is this feature that exponential of a times exponential of b is equal to exponential of a plus b, right? This, if you want, is an addition formula, like sine of a plus b, sine a plus sine b, you know what it is supposed to be. An exponential, this is very easy. If I have two functions, it's just the argument that adds. Most of the special functions don't do that. Right? So if I have a Bessel function, for example, k of a times k of b is not equal to k of a plus b. And due to that, the solutions look a lot more, it has a lot more clutter. This simplifies significantly. So things look very neat when you write in exponentials. If you're working in Bessel functions, then if you have worked with in electrodynamics, you might have worked with at least spherical harmonics, Legendre polynomials, and so on. You'll see that things don't exactly look nice. That's the only difference, but our ideas will remain the same. So that's broadly the idea. Again, let me just simply say this for completeness, is that this is you construct x comma x prime, and that's your delta function. And you can write your solution if this was x of t in terms of this. So that's a broad picture. So let me go back and let me talk about Green's function that we were doing yesterday or in the last class. And there, we completely did not, what I was trying to motivate you was that there is a lot of arbitrariness in Green's function when you're working on it. We worked with what we say is retarded Green's function, and then we introduced what is advanced Green's function. And I said the solution should be the same. It doesn't matter what coefficients you work with. And at the end, we did not have enough time and I could not finish it. So I'm going to finish that, and I'll take that opportunity to also show that that's not the only two Green's functions. You can have a whole class of Green's functions that you can build, and all of them will give you the same answer. With all the parameters that is free in there, it will give the same answer. So that's go. Any questions or comments on whatever I said on the function? You want to know more? Anything? Okay, if that help a little, give it bird's outer little zoomed out view of the next 2 weeks. Okay, so we were working on harmonic oscillator, forced harmonic oscillator, which has this equation irrespective of what this is. Have a differential equation which has solutions in terms of exponentials. The homogeneous has in terms of the exponential, and plus initial conditions x of 0 is equal to 0 velocity with this x dot of 0, that's equal to 0. If not for the forcing, that will be a trivial initial condition, nothing will happen. But if there is a forcing, then you can convert it. Immediately you write down your Green's function. Omega naught square T of T T prime is equal to delta function. And remember, T is the parameter that's crucial, and T prime is a point. Is a source. Like, I think it's good to think of T prime as a source. Like, it's a of like forced harmonic oscillation, right? What is a source of forcing? So this is a source at T prime, and T is an observer. Like, again, the words are coming from electrostatics. There is a charge and there is an observer, right? So you observe the electric potential due to the charge at some primed coordinate. The charge is sitting at x prime there. It's a position quantity. Here we are working with time. We said that this differential equation satisfies some differential equation. So we said, and there is a, let's say this point is P prime minus delta. That prime point is P prime plus delta, and delta is a positive number, infinitely tiny positive number, and we are sitting close to that. So we say this is P prime plus delta at P prime minus of P prime minus delta prime is equal to 0. And the derivative of Green's function, so G by dt, evaluated at T equal to P prime plus delta minus evaluated at T equal to P prime minus delta, that's equal to that's equal to -1. These two are called continuity conditions. Right? Called continuity conditions. Oh, is this readable? I forget that.
Yeah, it looks good.
A little bit. Hopefully better. These are continuity conditions, which means that these are derived from this equation. This was not given to you. If it was another differential equation, this may not be true. For example, a conductor, this may not be true. In electricity and magnetism, the boundary conditions associated with electric materials is different from the boundary conditions associated with magnetic materials. Electric materials usually have electric field 0 on the boundary, and magnetic materials have magnetic field 0, and that too in the tangent direction. So there is a lot of details in there. So there are modes associated in electrodynamics, but we are not talking about. Eventually, you'll get a differential equation, and that could be the boundary condition. We said G at T equal to T prime. Now that you have divided this a region of interest into two, T less than T prime and T greater than T prime, that can be written as A exponential of A I omega T plus B exponential of minus I omega T for T less than T prime, and C T plus B T prime. So this is like in this case, T prime is or T is greater than T prime, that's the right side, and T is less than T prime, it is the left side solution. Based on these boundary conditions, we immediately said that we can solve for at least one of them, and the solution we found was Look it up. We did this last time, so I'm not working this out again. I can write this here, right? Maybe. So this leads to C minus A. Okay, write down. Yeah, C minus A. Sorry. Yeah, C minus A came out to be equal to minus exponential minus I omega T prime, and D minus B is equal to also 2I omega. Plus and see the coefficients are always T prime dependent, because this has a T and a T prime dependence. The T dependence is captured in the exponential, so the coefficients always will be T prime dependent. That's your two equations, but there are 4 unknowns. So based on your whim, completely based on your whim, you can select which one you want to solve. In fact, you don't even have to solve for one of them. You can make linear combinations of this. We selected, in the first case, we solved for C and D. So in terms of that, you wrote here. Yeah, so there were 2 solutions we found, and I'm going to write that down, both of them here. This was, this is what we did last 2 lectures back. Was B e raised to minus I omega T plus, not minus. Because this step function tells me that T is greater than T prime. T is observer. T prime is source. So the source is always in the past. The observer is always in the future, right? So you call it a retarded Green's function, in the sense that retarded being the past is affecting the present, right? So this is called retarded Green's function. So retarded Green's function. This is a standard terminology. You will, whenever you see Green's function, that's the most popular Green's function. But that need not be the case. I can, as I said, this is a choice I made. I decided to solve for C and D. I could have solved for A and B, and then the solution will be in terms of C plus B e raised to minus I omega T. And in this case, this is plus theta of G prime minus T over omega naught times sine omega naught minus T prime. And this is called the advanced Green's function. But these 2 choices are very special choices. Here is a more general choice of T prime. You can have a whole series, right? Here it was T by, notice here it is T minus T prime. This is T prime minus T. You can have a linear combination of that. Part of it is this, part of this is that, right? So you can have a whole linear combination. So let me say, what could I call it? A, B, C, D, E. It's E raised to I omega T plus F e raised to minus I omega T. And I can have a linear combination, but instead of writing sine and cosine, it is good to write it as in terms of exponential. So let me give that to you. So the whole thing is minus 1 over 2I omega naught And a linear combination, notice where it is A and B, this is a different. That's minus. So again, so this is at the level of how much you want to understand. If you are struggling with the concepts associated with Green's function, in this course, for example, this is a beginning course, this is sufficient. You need only one Green's function. Work with this, that's good enough. You need one Green's function. If you feel very comfortable, oh, I understand this very much, then you go to the next one. Oh, this is also a solution. And then you realize that Green's function is not unique, there is arbitrariness in this. So that's the next one if you use. And then you realize that this uniqueness and arbitrariness is not just associated with one or two terms. There is a whole class A, B, C, D you can choose. And if you choose A to be 1 and C to be 1, then that's your retarded Green's function. For your choices of A, B, C, D, you get various Green's function, and at least 4 of them are very popular. They have names associated with it. I should also say here that A plus B has to be equal to 1, and C plus D has to be equal to 1. That's just for your information, and I'll mention something associated with it at the end. But let's talk about these two Green's function, which we already did already. Like we last time worked with these two Green's function and went ahead and solved for X, like the actual solutions for this, and we got alpha and beta associated with it. So let me write down those solutions. Any questions at this stage? This is the part where you solve for Green's function. That is still it's not complete, that is unknowns, but we still have the initial conditions, right? Unknowns will be fixed using initial conditions. There are 2 unknowns still left in this, which we will use the initial conditions to do that. Okay. Any questions on that, comments? Okay, so okay. Okay, so again, sort of you can see it here on the screen also. This is your initial condition, and my solution, the complete solution x of t is equal to the conditions for the Green's function and the initial conditions when you put it together. So you say this is e raised to I omega naught t plus beta e raised to minus I omega naught t plus your Green's function. That's your solution on this. E comma t prime times a. Again, the first 2 terms are homogeneous solutions. They will always be available, and they sort of fix your initial conditions. The Green's function helps you fix this. You would say that, oh, Green's function also has 2 unknowns in it, but those 2 unknowns gets added up with alpha and beta, right? They get mixed up and you define it as a new constant. So always you can get these things. Yeah. So let's talk about retarded Green's function now. So that's your general solution. And if we are working in retarded Green's function, oh, it's not readable properly. Okay.
So for retarded Green's function, we used initial conditions and found the alpha and beta. And we said this was alpha was equal to 1 over 2i omega naught.
Things like that. What am I? Yeah. We call it alpha prime.
And this is. Yeah, so this is minus infinity to 0, e t prime, and e raised to minus I omega t prime, a of t prime. And we also found that, let's start with alpha prime, just for the last time we found that alpha is better. And we also said beta prime is nothing but alpha prime's chart.
Complex conjugate, right? We did this last time, but then we did not observe one simple thing that I can combine just because they are the complex conjugate, and I left it there. I made basically it was my fault that I did not make that observation.
Because they are the complex conjugate, there is this nice feature that I omega t plus beta prime e raised to minus I omega t
It's equal to,
combine them. Notice this is a t dependence. It penetrates into my integral. So I have 1 over 2i omega naught minus infinity to 0 dt prime, and write this in the following form. Now there is an exponential. I write it as omega naught e minus t prime. The next one is a complex conjugate. So the complex conjugate associated with the coefficient gives me a sign, and I can write this as minus I omega naught t minus t prime and a of t prime.
like I failed to observe this simple thing, and that I redo it just so that there is a simplification. What is this function? That's a sign, right? In terms of exponential, if I include the 2i, that's sign. So it's 1 over omega naught minus infinity to 0 prime times sine of omega naught e minus t prime a of t prime. And also remember that g was equal to, oh, I should have written that also down, right? So g here, fit it in here maybe. So g of t prime, should have written this earlier. Niranjan, you should tell me if it is not readable, okay?
Okay. You can zoom it out. if
Zoom
you
it out
will.
is better, okay.
You can use the board like bigger space. Okay, that should work. Yeah, thank you.
This is
Minus, yeah, minus
beta t minus t prime sine of omega naught t minus t prime over omega naught.
Okay. So notice the same function sine is sitting there, sine is sitting here, so my x of my solution then has the simple feature that it is plus 1 over omega naught minus infinity to 0 dt prime sine of omega naught t minus t prime a of t prime, and I have, because of this minus sign and because there is a step function inside in there, this is going from minus infinity to t, right? Everything in the past is affecting.
That's why you say it's retarded green function, so it's dt prime, and there is a 1 over omega naught, write that down. Sine of omega naught t minus t prime over omega naught. At the Green's function, it is very meaningful to say it is retarded because all this minus infinity to t is contributing. But notice your initial conditions. This is homogeneous differential equation, notice. Right? This is a homogeneous differential equation. This is the particular Green's function. This cancels out part of it. Minus infinity to 0, minus in this is my, so this goes until 0 if you want. If that's a way of writing that. And then 0 to t, right? Like that's not a real thing at all, but you get my point that you go from minus infinity to 0 and then 0 to t. You can break that integral into t, add 2 pieces, and that piece cancels this piece. That's not a standard notation at all. Don't use it anywhere else. No one will understand it, but hopefully that makes sense. These two cancel out, and whatever is remaining is
Please,
oh,
move the
down.
camera. Thank you.
Now I think I can zoom. Is that okay? Readable?
Yeah, it looks fine.
I'll write it. So saving space, but now I have a. So this is minus 1 over omega naught, and it is 0 to t dt prime sine omega naught t minus t prime times a of t prime. And that's the complete solution with the initial condition. I introduced all the initial conditions, arbitrariness in the Green's function. After everything, I am getting what are the times, what are the sources contributing to it? 0 to t. That's it. Okay. Even the past, complete past doesn't affect it. Like it's only the source from 0 to t. T prime goes from 0 to t. Now we want to do the same thing for the advanced Green function. Again, we did most of the stuff. We calculated the initial conditions, contributions and all. But then it was coming out to be the future terms that is affecting. And we want to see how that goes through. So if I now do the future advanced Green function, do the same ideas here, but I'm going to do that on the other board, go all the way there. Any questions at this stage? Again, differential equation comes with an initial conditions. Introduce a Green's function without any boundary conditions. It gives you a solution. You have a choice. Pick the retarded one. If you don't know what you're doing, pick the retarded one. It leads to some arbitrariness. That arbitrariness is fixed using the initial conditions. Introduce the initial conditions, and usually it can be simplified together, and that's your complete solution. This is applicable, not, it has no retardedness feature in it. That's the solution, right? There is no arbitrariness in that. So we say that, oh, now do the same thing with advanced. We should reach the same place, or for that matter, this whole big arbitrariness we have, should be able to start from here and reach the same place. It should not matter how I do that, but let's at least do this for the advanced Green's function. And I'll write big. So advanced Green's function. Function is g of t comma t prime is we said c e raised to I omega naught t plus b e raised to minus I omega naught t. I did write that down. Rewriting it. And advanced in the sense that source or the observer is in the past. So this is in the past, right? Like past. And this is present. The source is coming after the event has happened. Like it's like saying you shoot a bullet and someone dies.
So someone dies and then the sugar is bought. So that's a dramatic way of.
Okay, so that's sine of omega naught t minus t prime. Okay. So we did this calculation and we calculated the alpha prime and beta prime. So x of t is equal to alpha prime e raised to I omega naught t plus beta prime, same beta prime plus minus infinity to plus infinity dt prime e of e comma t prime. It's here t prime, just copying it from there and using my c included in this, my alpha prime comes out to be equal. No, this is alpha, right? So it's not alpha prime, this is alpha. Alpha prime comes out to be in this case.
We did this last time, just pulling it together.
Minus 1/2 I omega naught. Look into your notes, you should see this. Prime and e raised to the prime. Notice no t dependence, right? Alpha prime is
Supposed to be
a constant, no time dependence. So it's after integration that is no time dependence. And beta prime was alpha prime star again. And again, nicely, if I put this all together, C and alpha all are together, I get alpha prime times e raised to I omega naught t plus beta prime e raised to minus I omega t. Remember, alpha prime is alpha plus the c that comes from this integral. Again, you did this last time. Okay, this comes out to be equal to, let's do this, right? So this minus 1/2 I omega naught 0 to infinity prime and I'm putting an exponential I. So this is exponential I omega naught t minus t prime. And the next one is star. When it is a star, first of all, I get a minus from here, so that's minus. And this is also complex conjugated. And the source. The forcing. Again, that is a sine function. With the two I included, so that's equal to minus 1/omega naught. This time, 0 to infinity. Earlier it was minus infinity to 0. This time it is 0 to infinity t prime and sine omega naught t minus t prime times t. What is the difference? Compare it with the earlier case for the retarded Green's function. It was minus infinity to 0. So this is the one that we are getting out of, like initial conditions are compensating it. So put this back in the solution x of t. And we have minus 1/omega naught now. Double focus. Change this in there. Zero to infinity prime. And the primary solution here, this goes in here and makes it a plus, so this plus 1/omega naught. And then t prime is greater. So t has to be, I think, so t has to be below, right? So t to infinity. The t prime is always greater than the observation. Notice this is all in the future, right? So there's a lot of, at least there's a lot of points in the future. So how do I do this? Assuming t is positive, this time I break this. Right, 0 to t, and then t to infinity. The t to infinity piece cancels this. And I again get the same answer, which is minus 1 over omega naught. So 0 to t e t prime sine omega naught t minus t prime. Point is that you can have all the arbitrariness you want. Eventually, when you fix them all, it is always going to come as the same solution, which is 0 to t. Anything in the Green's function construction, it seems like it's a future affecting it, but that's only in the Green's function part. That's not the complete story. There is a homogeneous part also that contributes to that. Unless there is a physical, if the moment you say that Green's function is physical, then you have to worry about it. But then if it's a physical, then there will be conditions on Green's function externally anyway. So then you have to look for more conditions on Green's function other than the continuity conditions. So that hopefully clarifies. And you can do the same thing with this also, but I think the time that remains, I will not be able to see we started. Like
The advanced Green's function doesn't satisfy the causality.
advanced Green function does not satisfy causality, but that's not the total way. That is this cohesive. The solution satisfies. Green function is a construct item. Right. Unless you're doing quantum field theory, their Green's function is physical. Like Green's function has a meaning associated with it. It's a propagator and it has real meaning in it. But then it has been upgraded to something like it's a P. It will have conditions on it. So it has two continuity conditions, and you search for two more conditions that you want to provide on the system. And that will again fix it. So always there will be two conditions from continuity conditions, at least second order differential equations, and two conditions that the system imposes. Here I'm saying that the Greens don't impose them. If you can, that's okay. There's nothing wrong with it. Often what I think that's what I began with. Often in the literature, you will see that the Green's function itself has conditions on it. Like, for example, retarded Green's function. You say that, oh, this should satisfy it. But the point I'm trying to make is that that's not complete. That's unphysical. You think that, oh, Green's function, why should that satisfy a condition? The conditions are on X. But it's okay to do that. If you directly do that, you will get the solution. That's perfectly fine. There's nothing wrong in it. It's just there is a slight change of discussion. And then you can see this retarded advanced here. The other one is called Feynman Green's function, which is half retarded, half advanced. Exactly half and half. Part of it is advanced, part of it is retarded. In that case, what you will choose here is if you set A equal to 0 and C equal to 1. So this is retarded and this is advanced. So in one part, you make it advanced, the other part you make it retarded. So if you make it exactly half, that's Feynman Green function. If you reverse it, that's called the Wheeler Green function. And then I come and say that that's all four extremes. You make a linear combination of them, then you have infinite class of Green functions. That's perfectly okay. It's kind of just nice to see that observation. Okay. And that's all. For change, we can chat or you can stop. Niranjan, comments, questions?
No questions. It makes sense.
And at least the Green's function part, these are typed. So you can
Like typically my lecture notes are not available in a narrative as such, like it's only recorded, right? So this happens to be available there. If you somewhere there is a link on the website. If I have not already put it, then ask me and then I'll put it. At least in one of the past websites there is a link. So if it helps, this was my, like, you guys have to do a, what is this called, qualifier? Yeah, right, so, and sometimes in universities, you don't not only do a qualifier, you also do what is, at least we call it specialist, like basically you work on something that's not related to your area of research for about 3 months, and then you present it, present your work on. So this is what I did for my specialist. So I had to type it up. Think so. Yeah. Okay. Okay, that's all.
It would be great if we can do some research problem with this green function. Sometimes
Yeah,
later.
actually, the whole of my research is Green's function, actually. So, yeah, the Casimir energy is the green. The trace of the Green function is the Casimir energy. How about that? If that helps.
I'm very excited to do something with this.
Yeah, let's do that. Yeah. Okay, thanks, Ranjan. Yeah.
Oh, we are done for today, right?
Oh, thank you.
Thank you, Dr. Sajesh.